So yeah, hi everyone. It's a pleasure to be with you virtually. So let me make sure I see you. So yeah, feel free to ask questions. It should not be a very buzzy talk. So try to discuss essentially the following questions. So what can we learn about black hole interiors from simple correlation functions like two-point functions and thermal field theory? Which certainly know about, in the context of photography, they certainly know about the geometry of the black hole and the exterior. And the question is, what do they know about the interior? And at least from where I come from, the question is more interesting the other way. So photographic theories are an example of a theory that you can actually study and that has strong interactions. And you can actually try to see if there are some general features that we can understand about the CFT correlation functions that we can calculate in these holographic theories. So actually, for me, the main motivation is this second one. The context of what we were discussing would be in large N holographic theories, and we'll be discussing essentially only single particle physics of WKB propagation in the bulk. So yeah, the paper is really just an paper I will discuss by these with these collaborators from last fall. Is really an exercise in WKB physics. So this is what we'll be discussing things that we call non-perturbative. But the non-perturbative in this WKB expansion, which is exponential of minus frequency times something at large frequency. So they're non-perturbative at large frequency, but they're not like e to the minus s type of non-positive effects that people often discuss in the context of black hole physics. So they're much more benign level of complexity. Okay. Uh, The starting point, I think this is not the typical starting point. The typical starting point of this subject are papers written in around 2005, 2006 by Schenker, Fitkowski, Ubeni, and collaborators. Sorry, I have the full list of others later. But actually, my starting point was a different one from about the same time, but surprisingly was not immediately connected. Is that in the context of ADS-CFT, you can calculate thermal functions. So, for example, the spectral function, which is the imaginary part of a retarded function, you can calculate it explicitly in various in holographic models, and you get curve like this in ADS-CFT. And of course, at high frequencies, you will expect that the high frequency mode doesn't really see the medium and you approach the vacuum physics. And that's the dashed line you see. That's a zero temperature correlator. And it makes sense to subtract them. And what you find when you subtract them is that, in fact, the difference decays exponentially small. That is a feature about these, that was what's found in this holographic theory. We see that it's not completely generic, but in this, for the stress tensors in 4 dimension, it happens. And so you see on the right, it's a log plot of the difference between finite temperature spectral function and zero temperature. And despite both of them growing with frequency, the difference decays exponentially. You also see that it oscillates. So that's why the dips are just when it changes sign. It's a log plot. And this is exponentially decaying difference. And that's basically this small difference. Trying to understand quantitatively the small difference will be our main goal. Uh, this was incidentally not the main point of that paper by Tini in 2006. His main point was to point out that the Euclidean functions, when you Fourier transform this to Euclidean time, it was almost independent of the coupling constant. So which is interesting implication for lattice QCD studies, which attempt to extract functions that look very similar, very different for real frequencies, but were surprisingly similar for Euclidean time. It was an important observation of that paper. Uh, so, so okay, let me quickly recap how these things are calculated. So in graph feed is a very clear recipe. I haven't drawn the bulk, but okay, imagine you have some, in ADS-CFT, you get an extra direction that's called U, a radial direction. And if you have a plane wave at the boundary, it becomes you have to solve some radial evolution equation in the bulk. And and yeah, you solve the equation, and you have to impose, in order to calculate the retarded function at the boundary, you have to impose infalling boundary condition that related to causality at the boundary of at the horizon of the black hole. And then to extract the boundary correlator, you take the boundary limit of this solution that's infalling, and the ratio of its two modes give you the retarded function. Okay, so it's very well understood prescription. And typically this radial equation does not have a analytic solution. You can still study it. It's a Hahn equation. It has nice properties. You can study it numerically or using various techniques. I will discuss briefly first a special case. It's nice to get intuition. It turns out that when you look at the two-point function of currents at zero momentum, this equation actually becomes simpler and can be solved exactly in terms of hypergeometric function. And then the retarded function is a very simple form that you can show that is basically given by this formula here. And the game we're playing here is that we're effectively expanding this at large frequency. So what you get from this is a sum of exponentially small corrections. And yeah, it explains nicely this plot. So the claim is that each of the term in this picture you can understand from a picture involving a bouncing geodesic. That's going to be the main claim of this talk. We can understand these terms from these effects. Notice also that here we're looking at the imaginary part of the retarded function. We look at other things later. But the imaginary part of retarded function is whenever you can draw a path, you can also draw its a time reversal path. It also contributes to the imaginary part. And the time reversal path will be something like this. And the path go from, say, a boundary point on the right to a boundary point on the left. The fact that it goes from right to left is why we'll come to it in a second. It basically why you can think of this exponent as exponential of minus I omega t, where t is the boundary term you go from that takes you. Can you see what I wrote? Yeah. So right, you can think of the exponent, this WKB exponent, as the time it took to go from one side from one endpoint to the other. And the fact that you have imaginary time of beta omega over 2 is just because you're going from the left to the right boundary. That's usual shift to go to the thermophile double. And the extra phase comes because there's a time shift of beta over 2 here. So in this is beta over 2 real and imaginary parts. So the phase comes from the real time shift here, which is non-zero because famously the Penrose diagram of a Schwarzschild ADS black hole in higher dimension is not a square. So you don't reflect at zero, the reflection at a different time. And when you take the imaginary part, this contribution can interfere with the other contribution. So there are particular frequencies where they arrive in phase, and there are particular frequencies where they interfere destructively, and that's why you get this dip. That's all there is to it. Okay. Just yeah. Okay. So the dip are very naturally explained by having this complex this geodesic and its time reversal. Okay.
Sorry, can I ask?
Yes.
So the arguments of the exponents are like 1 plus minus I over 2.
Uh-huh.
Can we actually in this expansion see some like higher exponents, like you see like with the argument 2 or 3 and so on, and what it would correspond to?
The extra one here, for example, that's what you're asking?
Yeah.
Yeah, these ones you can, so once you draw this picture, you can, you don't have to be absorbed by the boundary. You can reflect again and bounce back and so on. So there will be a geodesic here that has, roughly speaking, twice the exponent of the first.
Okay.
And you could keep bouncing and get the other ones. So it's very obvious that once you can draw this picture, you can draw more complicated pictures that explain the other exponents.
Thank you.
Yeah. Uh, in the full theory, so this example is very atypical because as we will see, in general, that's going to be maybe if I can anticipate the punchline of this talk. This is a very special case where the equation can be solved exactly, and this iron equation degenerated to hypergeometric. It's a very special case. In general, here there'll be a complicated function of frequency. And also this one here would be a complicated function of frequency. So this becomes some kind of A omega here, which would be an infinite series. In fact, an asymptotic series in 1 over omega plus this would be best understood as a kind of trans series. And there will be this reflection coefficient that we try to understand in general. So in the general, so we not just want to explain this particular formula in this special case. You want to understand uh, asymptotic series of this type that appear for general correlation functions, for example, of scalars with arbitrary scaling dimension delta. And also, yeah. Okay. So in general, in this more general case, it would be very difficult to go beyond this first two term. It gets like the general story of non-positive effects gets very complicated once you go. I mean, normally you focus on like if you just want to numerically understand the correlator, you just look at the first term. If you understand the first non-positive correction, you work a bit, but yeah, this is where we will stop in this analysis. Yeah, please feel free to ask questions. Okay, yeah. So there's a long history of people studying pictures that look like this, as I mentioned, going back from actually 2003, important work. And there's going to be a few distinctions compared to what we'll do today. So the original studies, the study, for example, fields with a large bulk fields with large mass, AV fields, and this gave rise to some space-like geodesic going into the bulk. Uh, and then they analytically continued this geodesic as a function of the boundary time, and they showed that there was some singular point, but it was on the second sheet of the correlation function. Uh, they've also shown that the similar signal shows up at large imaginary omega. Similar pictures also known to control I-harmonic quasi-normal modes. Roughly speaking, if I go back on this picture, you can understand the cartoon for a quasi-normal mode. You can ask, if you keep bouncing around this geometry, what's the probability that you end up in phase? And that all the bounds contribute in phase, and that is exactly the condition for having a quasi-normal mode. The WK, the semi-characteristic quantization is that after two bounces you end back in phase. Uh, it will be controlled by a very similar ingredient as what we'll discuss. So for example, there'll be this reflection coefficient A at the horizon, at the singularity, sorry, that appears. But in addition, there will be a reflection at the boundary that you need that is not relevant for our problem. But right, roughly speaking, to understand the quantization condition is that if you reflect twice at the singularity and twice at the boundary, you end up in phase. Right. So yeah. And this picture you can apply not only for black holes in ADS, but a similar picture you can also apply in black holes in flat space. Okay, where the wave bounce kind of a gray body factor reflecting out. All right. And great, yeah. So there's connections between these and other things. So the high frequency quasi-normal modes are related by same picture, as I just mentioned. What we will look at is something that's actually a different corner. We'll take small scaling dimension and large real frequency. And the main result, as I mentioned, would be the kind of a trans series. We have some parallel behavior from 0 temperature, plus high frequency expansion, plus some non-perturbative correction to it. Okay, and our main goal would be to calculate this precisely. All right. Okay. So I want to spend a bit Similar signals show up in a variety of things, so I want to spend some time just to explain the relation between different signals, different quantities one can consider. Uh, so let's just talk about the analyticity of Wightman function, of correlation function and finite temperature in general. Okay, so the simplest correlator to study are the Wightman function that have definite ordering, which you can calculate as a thermal trace, so like this. And you can also draw them on some kind of Schwinger dish contour, where A here is happening after B, so that's why they're in these different time folds. And here I'm drawing the Euclidean thermal circle as a circle. So this part here is a Euclidean time, and this part here is real time. Okay, right? This usual story where we prepare density matrix using Euclidean time evolution, and we glue real-time evolution to it. Okay. And if you just stare at this picture, it's very easy to see from QFT axiom that you get an LC in a strip. So you can add, if you add the imaginary part of to A that takes it down to this picture, it's like rotating along this thermal circle. As long as you don't rotate by more than beta, it's analytic. Okay, so there's the analyticity strip that the Wightman function satisfies. Okay, that's just guaranteed to you from like the path integral. Very clear. And and you can ask, yeah, before I ask what happens outside of it, let me say a bit more about this trip. So so the NC strip here is here. And the other concept I mentioned is the something that is often discussed is a thermophile double correlator, where instead of putting trace of e to minus beta h, you split it into two parts with half the exponent. And that is also well understood geometrically. That is like inserting if t prime is real, if you put a of t prime in there, this is like measuring something on the left boundary correlated with yeah. So the thermophile double state describe an entangled state of two CFTs, and this is correlation function of the left and on the right boundary. Okay, and this, of course, you can commute a across the exponential and just shift the time by complex amount. So in terms of this picture, if in the complex time plane, this is the usual, so this is the strip of analysis dimension between 0 and minus I beta. And the usual thermophile double correlator is exactly in the middle of that strip. So there are correlations there between the left and right boundary, but there are no singularities there. It's completely analytic there. It's right in the middle of the strip of analyticity. Okay, so so actually the bouncing geodesics are not at all on this strip. Nothing. The bouncing geodesic picture that I started with does not contribute at all on inside this strip. It would contradict these analytic properties. So, so the way we will find it is to go on a second sheet, the way that it gets revealed. So let me make some general comment. So if you're given a generic quantum system, an abstract quantum system, look at this two-point function. In general, there's nothing you can say about going outside of the strip of analysis. This is if you insert a complete basis of state, it's the sum diverge. There's nothing you can say. In CFT, we can actually say a bit more because we have a order product expansion. So if you take at this Wightman function, say for imaginary time, you can write it as a sum. The details don't matter so much, but it's an expansion of small x and tau, and the sort of unknown parameter are OP coefficients and 1 point thermal expectation value. So you replace a 2 point function by 1 point functions. And these are some Gegenbauer polynomials, spherical harmonics. So this, in CFT, this representation is known to converge, at least for real x and tau, less than the inverse temperature. Okay? And so this is very suggestive that actually you can go on the second sheet, at least when x and t are small enough, you should be able to go on the second sheet and talk about complex times that are outside the strip that I mentioned. Notice that it's not mathematically guaranteed immediately from what I've said, because if the sum were absolutely convergent, what I said would be correct. You go to second sheet, you add some phases to the sum, and it's still convergent. But in general, the sum is not absolutely convergent. You can have plus signs and minus signs. So in fact, the radius of convergence on the second sheet can be smaller than the first sheet. And in fact, this is what will happen. But generically, what we can say is the following. So, so, so in a relativistic CFT, you expect a branch point when t is equal to x on the like cone. And it's predicted by the OPE, and it has to be there. And the idea is that using the OPE, you should be able to expand around zero in a bit of a bigger region. So you should be able to push this cut up and start exploring outside of this axiomatic strip of analyticity. Okay? So this is the region of the complex plane that would be interesting to explore. And we'll be focusing on the region on the upper half plane. And notice that the region on the other side is basically it's KMS reflection, so there's no new information on the other side of the strip. KMS is the Z2 symmetry that exchange these two things. So yeah, so it makes sense at least in CFTs or I guess in well behaved enough QFTs to study what's going on in the second sheet. So why would we care about this complex plane? So basic picture, well, to me, the only reason I ever care about complex things, complex times or complex frequencies is that they can dominate Fourier transforms. So suppose I want to know the two-point function in frequency space. It's a Fourier transform of whatever it is at real time. But if the frequency is large, this is a very oscillatory integral and I cannot estimate it. The only thing I can do is I can try to deform the contour to make it smaller, follow a kind of path of steepest descent, and that way get an actual estimate for g of omega. So if you imagine a situation where you have some complex branch cut on the second sheet of the time plane, so if the frequency is large and positive, you see that it becomes advantageous. The integrand gets smaller, x bar omega t becomes smaller if you push t into the upper half plane, and the path of steepest descent goes directly on the vertical axis. So if you start from the Fourier transform that was defined on the real axis, and you try to estimate it at large frequency, you naturally lead to ask yourself, what are the complex singularities of this thing on the second sheet? So remember, so this branch cut here is what I'm drawing here. So I'm trying to push this branch cut up, but what can happen is that you discover a pole or another branch cut under it. So this is what happened is. So I'm pushing this branch cut up, and I've discovered that there's something else under it. And the idea is that this singularity starts at the time t0. It's going to produce in the Fourier transform a non-perturbative effect that goes like x of I omega t0, which is non-perturbative at large omega. Okay? So, so that's one reason to care about the complex time plane. It controls high frequency asymptotics, which is a thing we started with, saying that we're interested in. Okay, so the problem of understanding what are the non-perturbative effects and the plot we started with is equivalent to understanding what are the complex time singularities of this correlator. Yeah. I want to say something very general about this, which I don't know, this could have been said and in 2003, and it's just there's nothing new here, but I just want to emphasize something. This bouncing geodesic singularity, uh, that we drew it as a bouncing geodesic on the right. I drew it here on as a path on the actual original geometry, but actually does not exist on the original geometry. It is the original geometry describes things in the LC strip. The thing we're doing here when we're going to complex time is that we're taking one point here and going outside of the NLC strip means that we're taking this point here on the thermal contour and we're dragging it past the other. And then the path integral has to get dragged with it back and forth. So we're adding a very weird thing, which is, this the fact that in general there's no guarantee that the path integral doesn't converge here because you can never do backward Euclidean time evolution in the path integral. That's essentially the Koncevich-Segal criterion. It's the geometry that actually computes this bouncing geodesic that describes the singularity of the correlation function at complex times on the second sheet is a geometry that is like an analytic continuation of the original geometry. And effectively, the geodesic propagates on this part of the space-time, which is a bit of a copy of the original geometry. It's an analytic continuation of the exterior. We never actually seeing the original exterior, which is the point which would be on the left of this picture. We're exploring a copy of the left part of the geometry through a copy of the interior. Okay, that's a subtle thing, but this picture is never about actually understanding the original singularity. Okay, I wanted to state this immediately. Okay. So the other thing we can look at, besides the Wightman function that I mentioned, the retarded function actually has a very nice property. It's defined formally as a commutator, so it's a difference between two Wightman functions, so it has a similar analytic properties. So, or it has a step function. So in fact, it vanishes for t less than x outside the light cone. So it's supported from x and positive. Normally, it's a difference between two Wightman functions that have different analytic strips. So normally, it's only a distribution that's defined for real time. But as we just mentioned, if we can continue the Wightman function to the second sheet, then the retarded function will also be able to analytically continue from the real axis, from the positive real axis into some complex region. And the retarded function will have also this kind of a branch cut on the second sheet. And of course, the branch cut you find on the second sheet of the retarded function are the same as the branch cut you find on the second sheet of the Wightman function, at least if you don't go too far. Okay? Especially for singularities that are inside this original strip, the singularities are exactly the same. Okay? So yeah, we can also be talking about the high frequency behavior, the retarded function, but that it has a different structure. Okay? The retarded function does not have a strip of analyticity. And then in a abstract quantum system, it has no right to even be defined outside of the real axis. Okay. And here I'm showing also the steepest descent contour. So you would see that what you see is, roughly speaking, this vertical contour will give the leading asymptotic, and this other branch cut will give subleading exponential corrections at high frequencies. Okay, I'm saying a lot of things, but feel free to ask questions. So I will say a few more things about general things about correlation function, and then I describe the bulk picture. Okay. So one nice thing about the retarded function is actually its OP decomposition is much simpler. So if you think about a large N theory, you can decompose the operators which appear in the OPE of two operators, two single trace operator, as double trace and product of single traces. You need the product of single traces because they appear with 1/n coefficients. In vacuum, we'll neglect them, but the expectation of the stress tensor canonically normalized order n. So these cancel out, and all the product of stress tensor contribute at finite temperature. And then you have the double traces. There's a very nice fact that if you just manipulate the OP term by term, when you take if you look at the contribution from double traces, okay, it's not so obvious from this, but if you put delta prime equal to 2 delta phi, you see that this whole thing becomes polynomial. So double trace are just like polynomial, and the commutator is like a discontinuity, so the difference between two continuation of the correlator. It basically weight the same sum by a factor of a sign, which vanishes on the double traces. Okay, so the commutator kills all double traces, and that means that the retarded function emits an OP, which is saturated by single traces, product of single traces. Okay? So we're going to be assuming in a holographic theory where the only such operator that gets an expectation value is a stress tensor. So all the exponents which will appear in this thing are the dimension of the stress tensor, which is d times integer n minus 2 delta, this should be delta O, dimension of the external operator. So we have an OP of this type for the stress tensor. So it simplifies a lot. And even when you take degenerate limits, for example, if delta is equal to 4 or 2, uh, it could be that the double trace dimensions and the stress tensor are degenerate with each other. But in this case, the OP coefficient will diverge, but the sign factor will make it finite. So this sum is always well behaved, no matter what the scaling dimension is. So you always have a structure like this, where these coefficients A are finite, even in degenerate situations.
Excuse me, can I ask a question?
Yeah.
Yeah, so connecting, how would you connect that to the discussion you had in the previous slide where you were claiming that anything that a singularity can only happen by going to the second sheet?
Yeah.
Now, this feature doesn't seem to be, I mean, I don't know if you've ever
Yeah.
used the fact that
Yeah. No, yeah, that's a very good point. Exactly. So this let's see. If we start from the Wightman function, let's start from the Wightman function. Okay. Imagine we have an OP for the Wightman function. It has each term in the OP has a branch cut on the light cone.
Mhm.
And what I'm saying is that in order to calculate the retarded function, we need to calculate the difference between going below and above this branch cut.
Okay.
And because each term is a power law, taking this discontinuity, multiply each term by a sign factor. So retardant function is the discontinuity across this cut.
Mhm.
Normally on a real axis, but here you in this picture is deformed. But is a discontinuity, and that multiplies each term. So and normally you can only calculate this on the real axis.
Mhm.
But assuming that you have this behavior, you can deform things, then you can actually evaluate it retarded function outside of the real axis.
So this discussion of the OPE, this expansion that you had, was because you are effectively trying to expand around the light cone.
Yes. Well,
Okay.
or if x is small, it's the same as
Yeah.
expanding at small t.
Yeah, yeah. Okay.
Yeah. But the branch point happens to be on the light cone. But think mostly here as x is small. X could be 0 and everything I say could also work. Yeah, x could be 0 in this story. Yeah. So the retarded, so this OP motivates the idea that you can, this is a sum here. Yeah, it picks the various terms pick a phase, and if you go away from the real axis, this would pick some other phase. So basically you have a sum over something that converge on the real axis multiplied by phase that describes this retarded function away from the real axis. Yeah. And the other thing that is nice about just a technical thing that is nice is that you can Fourier transform. It's often in an holographic calculation, it's often convenient to go to momentum space, simplifies calculation. And so it's convenient, it will be convenient for the ball discussion. And because the retarded function is dominated for x less than t, then at small t, it makes sense actually to use the OPE, which is an expansion around small x and t. So actually the retarded function deserves to, as every right in the world, to have a OPE expansion. So at zero momentum as a function of time, as a sum over powers of t. Okay? If you did not take the retarded function, the Fourier transform will receive contribution from x that are very large, larger than beta, for which the OP makes no sense at all, and you could not say this. But the retarded function at small time and fixed spatial momentum is expected to satisfy an OP. Yeah.
But then, sorry to interrupt again, then you said that irrespective of whether you take the one or the other, the result would be the same, the second sheet. Isn't that right? It's
For
just
T
that
and
you wouldn't
X,
be
yeah,
able
yeah,
to see it from the OPE.
yeah,
That's
exactly,
okay.
yeah,
Okay.
yeah, correct. Uh, one feature here that is you can see also from Fourier transforming that if you do the Fourier transform term-wise, you do a Fourier transform in parallel, you get some gamma functions which grows factorially at large n. So basically the Fourier transform take a series which had a finite reducible convergence and turns it into a symptotic series at high frequency. Okay, that's just a basic fact about Fourier transforms. And physically, the time plane, like the Fourier transform is basically like a Borel transform at an I. So the T-plane is basically the Borel plane at large frequency. So what we're saying is that if you apply the OPE in frequency space, generally you only expect at high frequency to have an asymptotic series. You do expect a large omega, right? You do expect at large frequency, you do expect to see short distance and have an OPE. But in general, this would only be an asymptotic series. And what we're trying to understand, the complex time singularities, is effectively equivalent to understanding the Borel resummation of this large frequency OP. Yeah? So this is another way of saying what we'll do. Yeah. Let me also mention, maybe I can write something more here. Right. If I write this sum explicitly, for the Wightman, if I write the OP for the Wightman function here, let me just try to take this sum and forget the retarded function. Let's try to take this sum on the top to the second sheet. So G in general is a sum over single trace and sum over double trace. Like the Wightman function, say, would be a sum of two. And what will happen is that as you go to the second sheet, you make tau complex. Each of the term in these two things will pick a different phase. Okay? So the single trace will pick some phase that goes with this exponent, but because all the single trace have exponent 4n, let's say spacetime dimension is an integer, all these terms have the same, would pick the same phase, so you get something like exp of I pi 2 delta phi, or 2 delta O. So the single trace pick a phase like this, but the double trace pick a different, do not pick a phase when you go on the second sheet, when you continue. So what you would see is that the sum on the first sheet and the sum on the second sheet are dominated by essentially the same, by different phase. So understanding the singularity on the second sheet is understanding the singularity that's created by adding this phase is equivalent to doing the decomposition of the correlator into single trace and double trace. Okay?
So this would be a simple argument of why if you go to the second sheet,
yeah.
the Wightman boils down only depends on the
Yeah, exactly.
doesn't depend on the double traces, but just on
Yeah.
mildly stressed terms.
Exactly. And we can say even more. So the fact that the fact that the singularity cancel on the first sheet means that if you were to sum up the double trace contribution of the OPE on the first sheet, it would have to have minus the singularity as the other one.
Yeah.
So it's very clear that the same singularity show up in both these terms because the singularity shows up, because the singularity shows up here, but essentially the difference between computing the OP here above and the OP here below is just different phases. So the single trace and double trace have to cancel here on in the analysis strip, but if they cancel here, they basically have to double here on the on outside the strip. Yeah.
Thank
Okay,
you.
yeah. So physically, decomposing the correlator in single trace and double trace is equivalent to isolating the double trace using the commutator. It's equivalent to looking at a second sheet singularity. You can say all sort of words, and they are extracting the same information. Okay. And physically, by this steepest descent argument I mentioned, it's equivalent to looking at the correlator at large real frequency. Okay. So that's what this singularity dominates. Oops. All right. Okay. So, okay, let me say a few words about the WKB analysis. So historically, and this is very common, WKB is often used in the CFT for AV fields, so that have a large scaling dimension in the CFT. And in this case, the two-point function is typically written as a sum of the geodesics that are weighted by their length. But of course, the WKB approximation also works for massless fields, as long as you have a high enough frequency and it oscillates rapidly. Right? This is basically, like, optics is all about massless fields, right? So geometric optics has better work for massless fields. And this is more like what we will do because we imagining having a large real frequency. So that's where analysis will differ from the previous ones. So the starting point for WKB analysis of the wave equation in the bulk is to write down the Ward-Lang action for the fields in the bulk. And okay, the Ward-Lang action of a particle is minus the mass times its proper time, but you can write it in this form using Einbein. Okay. And then the basic quantity in that gives you correlation function is you fix two endpoints, find a classical path which go from one to the other, and evaluate the action of this on-shell path. Okay? And that is the Hamilton-Jacobi function, which is a function of the two endpoints of the paths. Okay? And for the paths I just described before, it's the mass times the path length. This action has some nice formal properties. So if you vary this action with respect to the position of the endpoint, you get the momentum at the endpoint. That's a definition of momentum. It coincides with Noether charge of the geodesic if you have symmetries, but this definition has nothing to do with symmetries. It's just the variation of the action with respect to position is the momentum. Okay, and the momentum defined in this way by the equation of motion satisfies the mass shell condition at any point along the geodesic in terms of the metric, local metric at this point. Okay. So P is a cotangent vector around the point along the path. Okay, so we can really think about, so we're thinking about just a classical particle moving in the bulk, and the Hamilton-Jacobi action will give us a solution to the wave equation from that. There's a subtlety that's important to mention in the massless case. What people do in the massive case is, so historically, the paper I mentioned earlier, 2003, what they did is they started from this two-point function that describe the correlation between the left and the right of the geometry. And then it has nothing to do with this bouncing geodesic, but then you start continuing it in the complex time plane, and then the solution is a function of this complex endpoint. Then you take the endpoint to the second sheet, and then you end up with a complex solution, and eventually you end up with a solution that looks like it bouncing off this singularity, okay, on the second sheet. So when you're talking about massive particles, you can continuously get there from a family of space-like geodesics. For the massless, when you're thinking about massless particles, you can't actually study families of paths like this. It's actually quite confusing. Because if you think about this Hamilton-Jacobi function, it's only defined when the on-shell path connects the 2 points, but the equation of motion for a massless particle tells you it moves at the speed of light. So an on-shell path exists only when the two endpoints are null separated. So for generic endpoints x, the Hamilton-Jacobi function is not defined, does not exist. And furthermore, when a solution exists, infinitely many solutions exist because you can rescale the energy and still a solution to the massless geodesic equation. Okay? So thinking about the Hamilton-Jacobi function, a function of position, this is a very bad way of parameterizing the phase space of a massless particle. For a massive particle, somehow the momentum and the position end up being function of each other, but that's not the case for massive. Instead, there's some better way to do it, which is to basically do, like in Hamilton-Jacobi formalism, you can do canonical transform as you wish, like Legendre transform here, and you can either fix the position of the momentum at each endpoint. So there's a function that's actually very nice. It's a very simple problem. You fix one point and one momentum. So basically you fix a reference surface, which could be the boundary. And so you look for geodesics which emanate from a point X and which cross this fixed surface with the given momentum. this always exists, well, generically. So there'll be, starting from x, there'll be some shooting direction where you cross the boundary with a prescribed momentum. Okay. So using this procedure, you define a Hamilton-Jacobi function. That Hamilton-Jacobi function you can define uniformly for massless or massive particles. A massive particle does not reach the boundary in finite time, in finite real time, but if you make the geodesic complex, it does. And so this is something we've discussed in a paper early last spring. So the picture is the following. So yeah, if you fix a bulk point x and you fix a boundary momentum p, there's in general a unique geodesic that reached from x that reached the boundary with the momentum p. This geodesic has an action s p comma x. And this action parameterized, for example, as you vary p, you will land on different points in the future like cone of x. And by taking the derivative with respect to p, you will read off what the boundary point that you land in is. Also, by taking derivative with respect to x in the bulk, you learn what is the shooting initial momentum you needed to get to the given place. So this was discussed in more detail in this paper from last January. Okay. So this Hamilton-Jacobi function that involves one boundary momentum and one bulk point is a very natural way of thinking about. It basically tells you everything about the optics of the bulk from the viewpoint of the geometry, from the viewpoint of the boundary for any bulk. Okay, we'll skip this. So we're thinking about this framework, and yeah, so generically these geodesics exist. And okay, I wanted to make a brief comment. This slide is a bit empty. If you think about a function of time and t prime, the basically you can go from one picture to the other by doing a Fourier transform, and when basically you'll get singularities, the correlation for massless field in the bulk, the correlation function will develop singularities at times t and t prime that are separated by a null geodesic in the bulk. And the singularity comes from the high frequency BA, from the fact that if these points are null, you can have an arbitrary high frequency that's going from one to the other. And then the Fourier transform goes to arbitrary high frequency that gives you a singularity in a slightly away. So we can also use this formulation to understand the singular behavior of correlation function in time domain when you approach a singularity. Okay. Okay.
So, sorry, do you claim here, would you say, because in the planar black hole, this is, in the black brane case, there are no reals at geodesics. So do you imply that you would see the singularities for complex ones as well, or not?
Yeah. So we see so the singularity is in this complexified geometry.
Mm-hmm.
And it's complexified because somehow this point here is at time I beta over 2 on the second sheet. But
No, I meant you refer to some other singularities
okay.
from your Hamilton-Jacobi. No, that was my feeling.
No, yeah, okay, sorry, let me come back. So yeah, what I'm saying here is just that so this branch point here correspond to the picture you can draw
Mm-hmm.
of the bouncing geodesic. And I'm saying that the information you're really calculating is the non-analytic part of the correlator. So if there's a pole, a branch cut, that's what you can calculate
Mm-hmm.
from WKB.
Uh-huh.
So you cannot calculate the correlator itself, but you can calculate
Yeah.
the discontinuity of the correlator.
Uh-huh.
So that's what this bouncing geodesic calculates.
Okay, thanks.
Thanks for the question. Okay, great. So how do we use it? So the idea is to actually evaluate this this path. Okay. So at the zeroth order, the thing that's most important about the path is its complex, is its action. And the action is basically the frequency times the time spent on it. And just a simple geodesic calculation tells you that the exponent will look like this thing that we're trying to explain. Okay, so it's very natural to try to explain these high frequency tails from a geodesics that look like this. One important thing that is especially blows up in your face when you try to do this for a massless particle is that now the geodesic is not smooth here. It just somehow has to bounce. And the reason it has to bounce is that close to singularity, the WKB approximation breaks down. So near there, we have to do something more refined and use the full solution. This is not different than when if you want to study light going from vacuum into water, there's an interface, and in the air you just have a plane wave. In water you have a different plane wave, and at the junction you cannot use WKB. You have to use the exact solution to the electromagnetic equation at the interface. And from this, you get reflection and transmission coefficient. Right? It's a classical story. So here's the same. There's going to be some kind of reflection coefficient that describes the physics from very close to singularity. And also near the boundary, there'll be some transmission coefficient for the WKB approximation breaks down near the boundary of ADS. But this is empty ADS physics. We understand now to calculate this very well. Okay, so basically WKB works, give you these straight line paths everywhere except near the endpoints and the reflection. Okay. So the hard part of the calculation that's not just in this exponential is this reflection. Okay. So our main proposal can be summarized in this one slide, which is the following. So in order to calculate non-positive correction to the to the to the to the retarded function or any correlation function, in order to define non-positive correction, we first have to define exactly the correction to what. So here what we mean by having a non-positive correction at large real frequency, we mean that if we take the naive Borel resummation of the series, which will be doing the integral along a steepest descent contour like this, it is not going to give us the exact answer, because the exact answer will be the Fourier transform done on the real axis, which will be the naive Borel transform plus a non-positive correction. That's what I'm writing below. So our proposal is simply that each of these terms have a specific interpretation in the bulk. So we know exactly how to calculate the retarded function, the standard retarded function, which would be the Fourier transform done on the real axis. We know that in the bulk, it's imposing infalling boundary condition at the horizon. Our proposal is that if you want to calculate this different solution in the frequency space, it's a different solution that just includes that vertical part of the contour. If you just want this, our proposal is just that steepest descent in the boundary maps to steepest descent in the bulk. And what is the steepest descent contour at high frequency in the bulk? The steepest descent lines are these dashed lines here. So if you start from large R outside the black hole, they take you not to the R equals 0 here as the singularity, R equal RH here as the horizon. The steepest descent line don't take you to the horizon, they take you to a weird copy of the horizon. Here I'm plotting a special case of 4-dimension, where the blackening factor is f of R proportional to 1 minus R4 over RH4. So this has a 0 at the horizon, but also, so probably RH4 or R4, probably the other way around. There's a 0 at the horizon, but 0 also at minus I times the horizon. It's copies of the 0. The lines of steepest descent, starting from large R, they take you instead from this point. So our proposal is that the thing which calculates at the boundary the Fourier transform of the correlator along this imaginary line, frequency space, and time domain, sorry, is exactly the solution to the bulk equation of motion that is regular at minus I fake horizon. That's our proposal. Steepest descent maps to steepest descent. So in practice, how do you calculate this? So we have to start with the solution that is regular at minus I. In order to connect it with the boundary, well, what we want to do is not just compare it with the boundary, we want to compare it with the solution that is infalling at the horizon. So we have to take this solution and connect it with the actual horizon. And this is not easy to do because you have to cross Stokes line, where something that's exponentially small here becomes exponentially big. So you cannot directly go from one point to the other. However, you can cross the Stokes line close to the origin where the exponent is not large. That's what we do. So we take this solution, evolve it to the origin, which is a singularity, and then use the exact solution near the singularity to cross the Stokes line. And then we can evolve along the real axis where it's oscillatory. And then compare with infalling and outgoing solution here. So for the case we studied, it was surprisingly simple. So the solution near the singularity, in terms of scaling variables, we take R to 0 and omega large with this combination x fixed. And the solution becomes the Bessel equation. And there's a particular one that is regular at minus I is the one that is decaying in the negative axis. And when you evaluate the solution that is decaying on this imaginary axis, you continue it to this real axis. You can just continue, which is an exact identity about Bessel function. You get a combination of Hankel function that are ingoing and outgoing. So, and then you continue it here, and it gives you some superposition of incoming and infalling solution. And the relative coefficient is what we call this reflection coefficient. So solution that is regular. So this regularity, so it looks a bit weird because it's minus I, but if you look at if you take a different coordinate that's like R square, it's a bit like a reflection of a wall. So you're imposing that the wave is decaying inside the wall, and then the outgoing wave is just a reflection. Yeah, impending wave with coefficient 1 and the reflected one with coefficient R. So that's what we're doing here. So this gives a boundary condition, which is a little bit weird because it's about this boundary is really the singularity is really a time slice. It's time-like boundary. It's not like a wall, but the mathematics still work out. So we get this reflection coefficient. So our main result is that the leading order reflection coefficient is -2 plus some. We also calculated the first correction. It was like 1 over omega to the 4/3 with the quotient we calculated plus other corrections. So what does it give? So yeah, once you understand this solution and how it's related to the retarded function, which is for doing the Fourier transform on the real-time axis, you can take the difference and predict this non-positive correction. So the result you can understand as a trend series. So the retarded function, that's a sum. So there's a leading saddle, that's this naive bow, that's this vertical axis contour, and then there's this first non-positive correction that we have here. And the coefficient of this correction is exactly the coefficient of a branch cut singularity at complex time. That's this thing. So that is our main result. We did a bunch of tests of it. So using a Fourier space variant of a method to calculate the coefficients, we obtained many terms in this small t series of this retarded correlator and zero spatial momentum. So we computed like 500 of these C's. And using these C's, you can fit the singularity. And actually, so this slide was old, but actually now this second check also works. So this number, yeah, this 2 here is exactly the -2 I mentioned a minute ago from the reflection coefficient. And this 5 is also predicted. This 1.4759 is also predicted. And then there are terms that we did not. So we
May I
discussed this.
ask
Yeah.
another question? Sorry to interrupt.
Mhm.
I was just wondering whether I'm not sure I completely understood, to be honest, your proposal for the boundary conditions, but I was wondering whether they have a relation to this Fitzpatrick and Huang method. I mean, in some way, you want to get rid of the double traces. Their
Yes.
method
Okay.
it gets
Yes.
all the data only from the boundary without
Yes. Okay.
going.
Yeah. There are many layers to your question. Thanks. Okay. So first of all, yeah. So 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 a first simple fact is that the OP for the retarded function, as I mentioned, the retarded function only has double trace in its OP. And the other nice thing about the OP for the retarded function is that, okay, if I draw like a DS geometry here at the top right, right? If you think about the retarded function at short distance, the retarded function is a causal thing, right? It's only non-zero when these 2 points are in the like cone of each other, but it also only explores physics in the causal diamond of these 2 points. So, so the retarded function, you can calculate its OPE without having to think about the boundary condition and the black hole at all. The boundary
But this
condition,
WKB solution that you had was not up for the retarded correlator.
yeah, the double kiwi was it's a contribution for a generic thing, but I'm discussing a check of this using the OPE.
No, I
Yeah.
understand. I'm just
Yes.
trying to think because the result that you get. So you
Yeah,
are
yeah,
able to observe the singularity of the correlator, and you
yeah.
could, in principle, observe it whether you would compute the retarded or the
Yes.
Wightman in the second sheet.
That is correct. Yes.
And this singularity is basically based on the stress tensor sector of the correlator, for
Yeah,
which, in
yeah.
principle, you can compute without going too deep in the bug. So I was
Absolutely.
wondering
Yeah.
whether this
Yeah.
WKB prescription that you have somehow has this information built in, because Fitzpatrick and Huang get all the data without going too deep in the bug.
Yes. Well, all of these C's, let me come back here. Yeah, so I'm not sure if that will answer your question, but uh, 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 the point is that the expansion around the OP expansion, which is expansion at small time, you can completely calculate using the Fitzpatrick-Kaplan, sorry, Fitzpatrick
Huang.
uh, uh, OPE that's use only the near boundary thing. And this is a finite reducer convergence, which in particular, its large order behavior tells you about the first non-positive correction.
Mhm.
So, so this is a usual thing in sort of when people talk about Borel resummation and trans series. If you know all the terms around the leading saddle, you predict the other saddles.
Mhm. Okay.
So this
I
is what
had
is
not
going
understood.
on there.
Okay. Thank you.
Yeah, but yeah, using only near boundary physics, you can compute all the terms here around the expansion around this point, and it gives you an expansion that converge up to the next saddle, the next cut. But instantly, this is actually an important point. This shows that the asymptotic of the OP coefficient, if you look at this distance, this point A actually is closer to the origin than the people often say that the asymptotics of the OP coefficient are dominated by the singularity of the at I beta of the Wightman function at I beta. But
Mhm.
actually, this singularity is closer.
Mhm.
So 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 the thing that really determines the asymptotic of the OP coefficients is this. But what happens is that this contribution on the principal sheet has positive contribution, say from the double trace, and negative contribution from the stress tensors. And it mostly cancels out on the Euclidean sheet. But still, it's the second sheet singularity that controls the convergence, the larger the behavior of the OP. So that is why using the Fitzpatrick and Wang recipe to calculate these C's using the boundary, we can predict this first singularity and it matches our prediction. So that's the main test of our procedure. We also have numerical tests that are in the appendix of the paper, but let me stop here. Thanks. Yeah. So yeah. So the main picture is that the main summary is that this can calculate retarded function at large real frequency in terms of transmission reflection quotient at the black hole singularity. This is a new thing, and this really these things are really defined by thinking about the mass and the bulk as being small instead of large. And the contribution we describe are non-perturbative in the sense that at high frequency they're suppressed by a half Boltzmann factor, but they're not non-perturbative in the sense of like E minus S or things like this. Okay, it's a relatively small price to pay. And if you're willing to pay this price, measure a two-point function accurately at large field frequency, you will learn about the interior geometry. But what you really learn about is not really the interior, it's an analytic continuation of the exterior. Okay, so we don't claim at all that this has any relevance for experience of infalling observer, the question of whether an infalling observer will experience a firewall. I think it's clear that none of this is relevant to this discussion. At least that's my opinion. I think that to me, there's one interesting conclusion about this, about CFT, which is that to me, what is actually quite exciting about this is not that there's a singularity there, but which is there's no other singularity. The retarded function, there's no other singularity. So if you put the cut here and here, there's no other singularity in a strip of size beta, I beta over 2. There's no other singularity here, which is kind of remarkable because from the strict viewpoint of thermal field theory, there's no reason to even be able to go away from the real axis at all. So it's quite impressive that there's a strip of analyticity. And for example, if you believe such a strip, using just a change of variable that do a conformal mapping of the strip to the disk, you can take the OP around time equals 0 and resubmit in principle to go to large time and make contact with hydrodynamics. So it's very surprising that in principle you could do this. So we don't know if that's true in general, and I think that's an important question. Right, so this is CFT two-point function, always analytic in the strip. So this will have implications for being able to resum the OP beyond its naive radius of convergence. And yeah, so this last comment was old, but it's about Uh, I I think it's clear that this if you do an initial state that is not a infalling black hole, it's not so clear what you exactly probe inside. It could be interesting to study. You can also start with two-sided correlator, uh, put some four-point functions, study some double traces. Joy Deep had a paper last November where he studied some of these four-point function ideas and show that you can get not just a singularity, but you can effectively measure the metric anywhere in the fusor wedge of the geometry. So I will stop here. Thanks for your attention.